RadTech innovators, and we've created a ground-penetrating device that detects buried metallic pipes via radio signals transmitted into the ground. With millions of aging and hazardous pipelines still in use, our solution helps cities accurately map and assess their infrastructure to improve city planning and public welfare.
Here we present to you a simple block diagram of our system. Our approach would be to develop a frequency-modulated continuous wave radar, or FMCW radar. We generate a sawtooth waveform and feed it into a voltage-controlled oscillator, otherwise known as the VCO. And now we'll present a video of our system in operation. We were able to obtain the B frequency of the pipe that is buried within our test bench. The pipe's presence is noted by the relatively fixed frequency at about 0.065 MHz, or 65 kHz.
Hello, we're RadTech innovators, and we're concerned about your health and safety. According to the EPA, up to 9 million homes to this day have their water supplied by lead pipes, which we now know is very bad for us. Not just lead, but aging infrastructure poses serious public health risks. We've created a ground-penetrating device that detects buried metallic pipes via radio signals transmitted into the ground. This will allow municipalities to map water utilities with hopes of identifying and removing pipes based on lead or other hazardous materials in a way that is accessible and cost-effective.
For concept development, we had different alternatives. Firstly, we had the electromagnetic locators, the ground-penetrating radar, and then finally the thermal imaging. After analyzing all of these alternatives, we decided to go with the ground-penetrating radar because it gave us the most accuracy and satisfied most of our objectives, which were safety, modularity, accuracy, and user-friendliness. We can see here to the right that we developed our electrical system algorithms and the design for pipe detection system. The power supplies powers the cable connections. The data processing unit will be the community radio running on an external laptop. The signal processing transmission will be RX, TX antennas, and the control unit is software-defined radio. For a final concept, we have two antennas that use GPR and software-defined radio to distinguish between two different material pipes underground.
Here we present to you a simple block diagram of our system. We divided our system into two halves. There's the software side, which is handled by an external computer running GNU Radio on Ubuntu, and there's the side of our signal pathway that is handled by the USRP 2901. The USRP 2901 is a software-defined radio, otherwise known as an SDR. SDRs offer significant benefits over traditional hardware-based radio systems, as it allows most signal processing tasks, such as modulation, demodulation, filtering, and frequency conversion, to be handled in programming rather than dedicated hardware. Our approach would be to develop a frequency-modulated continuous wave radar, or FMCW radar. Transmission starts at the chirp generator. We generate a sawtooth waveform and feed it into a voltage-controlled oscillator, otherwise known as the VCO, which contributes to the frequency modulation of our signal. Upon obtaining the reflected signal, we then mix it with our reference to obtain our beat signal, which is at a frequency that is specific to the source of reflection. Here's a screenshot of the software implementation of our FMCW radar. The entire system operates at a sampling rate of 20 MHz. A 1 kHz sawtooth signal is fed into the voltage-controlled oscillator, which produces a complex frequency-modulated signal that sweeps a bandwidth of 5 MHz. The signal is transmitted via the USRP sync block at a carrier frequency of 500 MHz and at a normalized gain of about 0.7. The receiver obtains the return signal and amplifies it to about 26 dB. Afterwards, the reflected signal is low-pass filtered to eliminate the higher frequencies above 10 MHz before it is mixed to obtain the beat signal. And now we'll present a video of our system in operation. As you'll be able to observe later, we were able to obtain the B frequency of the pipe that is buried within our test bench, which consists of a 20-gallon tank filled halfway with soil. The pipe's presence is noted by the relatively fixed frequency at about 0.065 MHz, or 65 kHz.
dealt with cracked pavement or uneven roads, our product RootSeek can help deal with that. RootSeek sends RF signals down to the ground and back up to itself to understand where the tree roots are underground. As well, it has temperature, humidity, and soil moisture sensors that help you understand the root's health for better extraction.
With RootSeek, you want to place it on the ground at your desired location with the antenna position 180 degrees opposite from each other and making sure it's even on the grass. Then connect the sensors to their power source and the GPR to your computer of choice, which will run the user interface and GPR software. Once everything is connected, start the system. You'll see it operating through the user interface and view the results in real time. Using the results, you will find the root of your problem and be able to solve it before the real damage.
Bro, you good? What happened in there?
There's a gas leak in there, bro.
Yeah, it's because you went in there with no protection.
Got my hard hat, though. What'd I do?
People in these kinds of work environments are always exposed to hazardous gases that can cause a myriad of health risks. AeroGuard is here to prevent that. This is AeroGuard, a wearable gas detection device powered by 4 AA batteries and has Wi-Fi connection to protect workers in high-risk environments. AeroGuard monitors harmful gases like carbon monoxide, methane, carbon dioxide, and measures oxygen volume in real time. AeroGuard also has an audio and visual alert system, protecting users from harsh gas conditions. We are not only confident, but guarantee that these features will help AeroGuard work hard for the hard workers.
Man, good thing I had AeroGuard, man.
But you're missing one important thing.
What's that?
Your hard hat, though.
AeroGuard, protecting lives one breath at a time.
Meet AeroGuard, the next generation of wearable gas detection technology engineered to protect workers from high-risk environments like mines, oil refineries, and industrial facilities. What do they all have in common? An invisible enemy. Gases such as carbon monoxide, carbon dioxide, methane, and even oxygen. Gases that at a moment's notice can change a situation from hazardous to disastrous. AeroGuard is here to fix that. This is the device. It's supported by an ESP32 microcontroller and powered by 4 AA batteries, measuring up to 6 volts and 2000 milliamp hours of capacity. The device has 4 main gas sensors: the oxygen sensor, the methane sensor, the carbon monoxide sensor, and the carbon dioxide sensor. Their values are being processed and then displayed onto this OLED, which allow you to view values in real time. There's an onboard LED and a buzzer for a combination of audible and visible alerts, as well as an SD card underneath for local data logging. Additionally, the ESP32's built-in Wi-Fi connectivity allows for seamless data sharing for team-wide awareness via the Lassonde dashboard. The best part? The straps, which make the device wearable and usable in many different work environments. In terms of the concept development, we had originally gone with our first alternative, which consisted of duty cycling and sleep mode, modular sensors, contextual alerts, and a USB interface. The disadvantages being that it was limited in interfacing due to only being USB. It possibly might have calibration issues or be slower at reading because of the extended sleeping, so we decided to go with this alternative that consisted of sleep mode and MOSFET switching, a built-in sensor array, multimodal alerts, and an SD interface and the Lassonde dashboard. Advantages being that the sleep mode with the MOSFET switching reduced the power as much as possible for some of the very power consumptive sensors. The multimodal outputs, that being the visible LEDs, the audible buzzer, and also the visible OLED, boosted awareness to the max, with the built-in sensor array being a little simpler to design and implement, and the SD card allowing for offline data logging. Disadvantages, it wasn't modular, and not being modular lowers the replacement and repair cost, and the SD interface might not be as practical or accessible as a USB interface might be. In terms of the final block diagram, as you can see that there's a power block that powers the ESP32 with a 5-volt buck converter, steps down the voltage from the batteries down to 5 volts. There's the GPIO header, which powers all the peripherals. There's 2 sensors that are analog and go into the ADC. The other two sensors are I2C and send out digital signals. The OLED display communicates by I2C, so those three peripherals are an I2C bus. The SD card reader is SPI, and the buzzer and the RGB LED just go directly into GPIO pins and are pulled high, and they are visible and make noise. And then there's the Wi-Fi module on board that connects to the Lassant service, and that's how you can view Lassant remotely.
Some working environments require you to train using dangerous materials. With Field Tech, you won't need to worry. Field Tech will protect you from this danger. Hi, I'm Dior Rosario Class, and I'm part of the team here at Field Tech. Our weight glove is professionally designed to realistically simulate an object's weight in a virtual environment. Just put on our glove and backpack, connect it to your virtual reality system, and get immersed in a world where virtual objects meet real weight. With Field Tech, you can learn, enjoy, and experience VR like never before.
Some jobs involve training with hazardous materials, but not with Field Tech. We take the risk out of the equation. My name is Mateo Rojas, and I'm part of the Field Tech team. I'm excited to introduce you to our cutting-edge weight glove. It's engineered to bring the sensation of real weight into your virtual world. Just slip on the glove and the backpack, hook it up to your VR system, and step into a space where digital objects feel amazingly real. With Field Tech, you can train smarter, explore deeper, and experience virtual reality in a whole new way. The hardware components of our system consist mainly of a backpack and the actual glove. Inside of the backpack, you're gonna find a 3D printed casing with a set of pumps and its own microcontroller. And also you're gonna find the reservoir for the liquid. Inside of the glove, you're gonna find a pouch like this one with a respective straw for better flow. You're also gonna find a tracking system on top of the glove, which is this one that you can see over here. For our initial design, we had 6 different categories that we needed to design on. First one is the VR engine, then microcontroller, a fluid, haptic feedback system, power source, and an interface. Based on the constraints that we had in our proposal, we designed to work with Unreal Engine first, since we already had experience with it. Based on previous projects, we knew how to work with ESP32 microcontrollers and how to connect them to Unreal Engine. After making some tests with different fluids, we came up with 4 possible solutions: water, gallium, mercury, and silicone oil. Based on our constraints, we decided to go with water, since it's safe for the user and it's easier to work with. We considered different types of pumps for our system, from electroosmotic to diaphragm pumps. Initially, we decided to go with peristaltic pumps, but the flow rate was very low for our needs, so we decided to change it to diaphragm pumps. For power source, we had 2 options: a portable battery and a wired connection. Since we wanted our users to be able to move around with their system, we decided to go with a portable battery of 12 volts. Based on the same constraints, we decided that our interface should be a backpack instead of a grounded station. In this final block diagram, we can observe how our system works in general. First, we have Unreal Engine, which controls the interaction of the user and the simulation. We have attached a variable for weight to each one of the objects inside of the simulation. This data is then sent to the ESP32 microcontroller in the backpack of the user. This ESP32 microcontroller then sends a signal, a time-modulated signal, to different MOSFETs or set MOSFETs in the backpack. Using the power supply of 12 volts, we powered the diaphragm injection and retraction pumps on our system. These pumps are connected to a liquid reservoir that's also in the backpack, and on the other end is connected to the gloves pouch. Having two sets of pumps allow us to have a higher flow rate. The ESP32 microcontroller is also in charge of converting the data as a weight variable into a time variable that then is going to be sent to the MOSFETs. These MOSFETs then control the diaphragm injection pumps and the diaphragm retraction pump set, which are powered by the 12 volts power supply. These pumps are connected to the liquid reservoir and the gloves pouch. This dynamic connection between the pumps and the glove creates a weight sensation that the user can compare to a real sensation of weight. Tracking systems integrated into VR systems currently work detecting the hand shape of the user. Since we are covering the user's hand with a glove, it's impossible for these systems to detect the hand and track it accurately. Therefore, we have decided to create or attach our own tracking system that runs in parallel to the weight system. This tracking interface was created by Asterisk Systems in collaboration with Y12.
Imagine you could have MP3 playback, a built-in mic, customizable sound effects, and audio manipulation all in one. Well, now you can with the Sonatio sound effects system. From streaming to live events, you can take anywhere you need to. So first, have an SD card loaded with the MP3 files and the sound effects that you would like to play. Plug it into an outlet, and as you can see, the screen is on, so I can play a file now. As you can see, it's coming out of the speaker. I can lower and raise the volume with the potentiometer. Here's a vent for airflow, and here's me testing the mic. So in the background is a video of me going through different modes. So the default mode is MP3 playback mode. The first button of the second row, which is the mode buttons, changes the mode to mic mode. The second button changes it to sound effect mode, which allows you to select the sound effect. The third mode is audio manipulation mode, which allows you to apply filters to the sound. And the last mode is browser mode, which allows you to choose a clip from the list of MP3 files that you have on the SD card. Imagine you could have MP3 playback, a built-in mic, customizable sound effects, and audio manipulation all in one. Well, now you can with the Sonatio sound effects system. From streaming to live events, you can take anywhere you need to. So I'm going to go over a little bit of the early timeline, and if you're the reason why the final prototype ended up looking the way it did. So early on, we had three options. We had an option with an Arduino, microphone, and headphones. This was quickly discarded because the Arduino was more expensive than another option that we were considering. The second option was an STM32, a MIDI controller, and an amplifier. Again, the STM32 and the MIDI controller were looking very promising, but the higher cost to our third option and the complexity drew us away from this a little bit. This third option was basically what we ended up going for. It's an ESP32 with button controls and an amplifier. So the ESP32 provided an inexpensive and low footprint power-wise and space-wise for prototyping. One thing that we were worried about early on was the marketability and making the product stand out in a saturated market. So we decided to implement as many features as we could to attract it as we could.
This is the final block diagram for the Sonatio sound effects system. In the middle, you can see the ESP32, which is the brain of our project, and connected to it are all of the components we're using. So we have a 4x4 matrix keypad, a potentiometer, a micro SD card adapter, an OLED display, a microphone, the power adapter from 12 volts to AC to DC, and the breadboard power supply module which we used. For inputs, the user inputs are read with the 4x4 matrix, where the user can push buttons to choose the mode and what he wants to do, like pause, play, speed. We have inputs from the potentiometer for the playback volume, and then we have inputs from the microphone for live audio capture. The outputs are handled mainly through the MAX 98357A amplifier for sound, and the SSD 1306 OLED display, which it's used for the user interface. Signal flow, we have power entering from the DC adapter and is regulated to 5 volts and 3.3 volts using the breadboard module, supply module. The signal is processed with the ESP32 microcontroller. It handles digital input readings and audio files.
So first, have an SD card loaded with the MP3 files and the sound effects that you would like to play. Plug it into an outlet, and as you can see, the screen is on, so I can play the file now. As you can see, it's coming out of the speaker. I can lower and raise the volume with the potentiometer. Here's a vent for airflow, and here's me testing the mic. So in the background is a video of me going through different modes. So the default mode is MP3 playback mode. The first button of the second row, which is the mode buttons, changes the mode to mic mode. The second button changes it to sound effect mode, which allows you to select the sound effect. The third mode is audio manipulation mode, which allows you to apply filters to the sound. And the last mode is browser mode, which allows you to choose a clip from the list of MP3 files that you have on the SD card.
Introducing our RFID inventory management system. We will be using RFID technology in order to be able to take inventory of items wirelessly, making it easy and efficient to take inventory for items without having to use manual tracking methods like barcode scanning or manual counting.
Hello, here's our demonstration setup. So what I have right now is the custom-made RFID tag reader, and these are the tags themselves. So to demonstrate, what we're going to do is place the tag inside of this box, and then we are going to scan for it using the reader and verify that it is within our inventory.
I'll start by opening up the reader application and inputting the name of the tag that should be attached to the desired item. The reader will transmit the signal specific to the desired tag. After transmitting the signal, the reader will switch to the receive mode to accept the confirmation signal from the tag and let us know if the requested items are available. Introducing our RFID inventory management system. Long gone are the days of using manual tracking methods in order to track your inventory, such as walking around and counting individual items or checking things off of a checklist, or using a barcode scanner to individually scan each barcode of your items. Long gone are those days. With our system, you can use RFID technology in order to track your systems wirelessly. We provide active RFID tags in very strong and compact, durable cases that can take any sort of punishment and still operate, as well as providing you with a user-friendly reader that you can use in order to walk around and take inventory of your items wirelessly. For the concept development of our project, we looked at 3 different RFID tags. For the first design, we looked at a passive chipless RFID tag. However, we did not go with this design because it proved very costly and difficult to research and develop, as when you make a circuit, you can't reprogram that RFID tag. We also looked at a battery chipless design, but that had the same problem of once you develop the circuit, you can't reprogram it. The design we decided to go with was a battery and chip design. This allowed us to reprogram the RFID tag and come up with our modulation schemes.
Here's a quick overview of the final block diagram for our RFID inventory management system. We have 2 main sections. the RFID reader on the left, and the RFID tag on the right. First, the reader. The system starts with receiving the user input, which tells it which item to scan for. This data is displayed on the touchscreen, allowing the user to interact with the inventory application. Both the touchscreen and the reader's core component are powered by the internal battery, ensuring that the system is portable. At the heart of the reader is the Raspberry Pi 4, which handles all the processing, such as running the inventory management software, interpreting user control, and preparing data to send. When it's time to communicate with the tag, the Pi 4 sends signals to the CC1101 transceiver, which converts these digital signals into RF signals. The antenna then transmits these signals to the tag. Over on the tag side, we have a battery-powered Raspberry Pi Pico, which is a smaller microcontroller that handles the basic operations like responding with its own stored data or updating the item information. Similar to the reader, the tag has its own CC1101 transceiver to receive signals from the reader and send back responses. The antenna on the tag is what enables that RF link. In terms of signal flow and processing, the user commands flow from the touchscreen into the Pi 4. The Pi 4 processes the instructions and sends them out via RF. The tag's transceiver receives those signals, and the Pi Pico processes them and returns the inventory data. This data goes back to the same route to the reader, where it's displayed and stored. Now here is a demonstration of our product.
Hey Aiden, do we have any LCD screens in stock? I need one for a project I'm working on.
It should be tagged with our RFID tag, so I'll check using the reader now. I'll start by opening up the reader application and inputting the name of the tag that should be attached to the desired items. The reader will transmit the signal specific to the desired tag. After transmitting the signal, the reader will switch to receive mode to accept the confirmation signal from the tag and let us know if the requested items are available. Yeah, the reader says that they should be in stock. We usually keep them over there.
Sounds good, let's see.
Go. And this is how we knew they were in stock.
Oh, that's pretty cool.
We just took a look at the current process FPO uses for face verification. They came up to us, Skyward Panther Solutions, in order to make improvements to that process. We're working on increasing the efficiency and reducing it to be a one-person process and reduce the need to mobilize trucks, since in the video it wasn't shown, but sometimes a truck is needed to mobilize to reach the power lines. The way this process would work now, we would attach this system into the drone that would go up, take it up to the power line, and it will get a reading. Then the reading will be sent to the ground unit, which will be attached to the controller of the operator. Now here are some takes of our solution being tested on FPL grounds. Here we have our wireless transmission system. What we essentially created is this Raspberry Pi in here is going to be covered in order to be able to be taken into flight, and it has a camera running an OCR model and a receiver, which is listening for whatever information is being transmitted from the sender. Let's take a closer look at each individual moving part. Starting with the receiver, we created a private network at which it's trying to listen for any information being sent by the facing unit. Now, whenever a reading takes place, it tries to instantly send it as quick as possible. The reason why we get a no valid reading sometimes is because the transmission is not seeing any changes, so it just sends a message announcing no valid reading, and then it updates itself to the correct reading. Now, let's look at the facing unit itself. In the facing unit, we have a cover for our Raspberry Pi that essentially has the camera inside, and it allows it to go in the flight. Let's take it apart so we can have a closer look at it. Starting with it, we have a Raspberry Pi with a fan on it. The fan is working for ventilation in order to not have it overheat. And here we can look at the camera being connected, looking directly at the facing unit screen, and then gathering whatever data it gets from there. Now, let's have a look at the scripts themselves. Essentially, the way we run the script is it takes a picture of whatever is seen on the screen, and then it processes it to make it readable. It runs an OCR model, and then this OCR model transmits the data into the receiver as shown.
Now let's go over our previous concept designs and how we arrive at our final conclusion. Our original design started with extracting data directly from the sensors of the phasing unit or rerouting it through the Raspberry Pi. Due to firmware restrictions from EDM Labs, however, we couldn't move on with either method. We also were exploring two different power sources of trying to use solar and battery or battery packs. Solar ultimately was ruled out because it didn't supply enough power for our needs. Then, when we were considering the different transmission protocols, we had ESP now and just a direct Wi-Fi connection, depending on the microcontroller. However, when we chose Raspberry Pis, ESP nows were not compatible anymore. Then we planned for different types of enclosures, either strapping it onto the back of the phasing unit or onto the drone itself. However, once we move away from direct data extraction, this setup was no longer feasible. All of these constraints ended up leading for us on our final design, which was using an OCR model to capture data visually, and then an enclosing placed in front of the phasing unit facing the screen to transmit the data down to the ground unit. We can also now see our final design implemented and shown on this final block diagram. To start, an FPL technician is going to control our drone via a handheld controller, and mounted onto the drone is going to be our phasing unit with our wireless transmitter, and then onto the screen of the controller, we're going to have our ground unit. The transmitter is going to include a Raspberry Pi powered by a battery pack and is going to be cooled with an active fan and connected to an IMX500 AI powered camera. This camera is going to capture images of the screen every 5 seconds, and then we're going to use an onboard OCR script to process these images in real time. With this, we can confirm that our readings are 100% accurately, and then we're going to wirelessly transmit them over a Wi-Fi network with our ground unit acting as a hotspot. This connection is maintained through an opening listening port. Housed inside of the ground unit is going to be a Raspberry Pi 4, which is also battery powered and is going to be equipped with an antenna to boost the signal, and a GPIO LED display in order to output the readings. The receiver is going to be able to mount this antenna directly into the drone controller for easy access and reading the information.
Good afternoon. My name is Jacob Stafford, and I'm a part of Team 10. We are making a battery prognostic and diagnostic tool. This will help predict and diagnose when batteries are starting to go bad, and help the average person keep their batteries healthy. We use advanced machine learning algorithms to predict the state of health of the battery with the collected data from the BMS. This information is then shown in a user-friendly interface.
Welcome to the interface of our battery diagnostic and prognostic tool, a full-stack application designed to deliver real-time insights and intelligent predictions for battery performance. At the top of our dashboard, you'll see two key indicators, state of charge and state of health. These display both the current values as well as the predicted states 12 hours into the future. Moving down, we have the battery metrics over time graph. This chart visualizes 4 key metrics: actual state of charge, actual state of health, the predicted state of charge, and predicted state of health. To the right is our control panel, which bridges the user interface with live system control. Here, users can toggle the system on or off, and once the state is selected, clicking Send Control Signal sends either a 1 or a 0 to our DynamoDB table. In our user control table on AWS, we receive a signal of 1, which is displayed here. This one runs a specific script on our Raspberry Pi, which begins logging live data from the Orion BMS. This raw data is then stored into a database known as raw data, where it's later processed by our machine learning models. These models generate predictions and uploads them into our predictions table here, which then feeds back into this dashboard. Altogether, this system connects user-driven control, real-time monitoring, and intelligent forecasting into one intuitive platform.
Good afternoon. My name is Jacob Stafford, and I'm a part of Team 10. We are making a battery prognostic and diagnostic tool. This will help predict and diagnose when batteries are starting to go bad, and help the average person keep their batteries healthy. We use advanced machine learning algorithms to predict the state of health of the battery with the collected data from the BMS. This information is then shown in a user-friendly interface.
This is going to be an overview of our whole hardware portion of this project. Here we have the battery pack that holds 48 volts with a current sensor over there. Over here we have the Orion BMS that is reading data from the battery pack. On top of the Orion, we have the Raspberry Pi, which is collecting data from the BMS and sending it to the cloud. Here we have our 2 relays, which is differentiating between charging and discharging. Here's the transformer we use to power the relays. These are 2 resistors we have in series in order to act as the load for our circuit. And here are the 2 chargers we're using to charge the batteries. Finally, we have 2 DC power supplies over here. This one is acting as a charger to close the relay, and this one over here powers the Orion BMS and the transformer to step it up for the relays.
Hello, this is Franco Sanabria, and in this demo, I'm going to be showing the MQTT layer. So as you can see, I'm going to run the start stage command that's going to start getting the data that is already stored in the Raspberry Pi. And as you can see here, the MQTT is receiving those messages constantly, as you can see in the data time and in the portal. And in the same time, this data is being uploaded into a database. As you can see here, hold on, I'm going to show you right now while it's loading. As you really saw, it was only 6 items, not 16, after sending all this data. So everything is being stored here. And after it's being run in the EC2 instance, the EC2 instance is also sending the data that is the predictions to this database.
Hello, my name is Joshua Natal, and what you're seeing here is a look inside our AWS EC2 instance, which serves as the environment for running our machine learning model predictions using live BMS data. I've launched the Jupyter Notebook on this instance that processes CSV files generated from a Simulink simulation of our BMS setup, as you can see here. These files contain simulated data that we use to train an XGBoost model across various charge and discharge cycles. Once the model is trained, we test it using real-time BMS data. The model's predictions are then pushed to a DynamoDB table, which serves as a backend for forwarding the results to our user interface, as you can see here.
Welcome to the interface of our battery diagnostic and prognostic tool, a full-stack application designed to deliver real-time insights and intelligent predictions for battery performance. At the top of our dashboard, you'll see two key indicators, state of charge and state of health. These display both the current values as well as the predicted states 12 hours into the future. Moving down, we have the battery metrics over time graph. This chart visualizes 4 key metrics: actual state of charge, actual state of health, the predicted state of charge, and predicted state of health. To the right is our control panel, which bridges the user interface with live system control. Here, users can toggle the system on or off, and once the state is selected, clicking Send Control Signal sends either a 1 or a 0 to our DynamoDB table. In our user control table on AWS, we receive a signal of 1, which is displayed here. This 1 runs a specific script on our Raspberry Pi, which begins logging live data from the Orion BMS. This raw data is then stored into a database known as raw data, where it's later processed by our machine learning models. These models generate predictions and uploads them into our predictions table here, which then feeds back into this dashboard. Altogether, this system connects user-driven control, real-time monitoring, and intelligent forecasting into one intuitive platform.
We here at Agritech have one purpose: to give farmers a simple solution in order to monitor the health of their crops in real time. With the help of our smart monitoring system, you'll be able to quickly place multiple devices across your field and access helpful data such as temperature, humidity, and light from anywhere in the world.
This is our Smart Agriculture Sensor node. We place it next to the plant to begin monitoring environmental conditions like soil moisture, temperature, humidity, and light. The solar power system is wirelessly connected via LoRaWAN, which can rate up to 1 kilometer from the hub. Once powered, the sensors collect the data and transmit it to the gateway. Here you can see the real-time sensor values appearing in the console, confirming successful data transmission from the field. The data is then sent to a cloud-based server and displayed on a web app. This interface shows live updates from the plant environment, helping users make informed decisions instantly. The system is simple, efficient, and wireless, so you can farm smart.
Agritech is more than just a green logo. We care about plants and want to make tending them easier and more efficient. So we did just that. Our latest project is a smart agricultural monitoring system that lets farmers, field researchers, and even home gardeners check the status of their plants day or night, anywhere with an internet connection. The setup is simple. Connect the gateway to the internet within range of the plants you want to monitor and place one or more sensor boxes on the soil near the plants. Then check the app for real-time data or ask the AI assistant for a breakdown.
Our concept selection started in Senior Design 1 when we compared 3 design approaches, LoRaWAN, cellular, and Sigfox-based protocols. We applied a weighted scoring system considering cost, power usage, scalability, and overall feasibility. The LoRaWAN-based system emerged as a top choice with a weighted average score of 4.49 out of 5, offering the best balance of long-range communication, low power consumption, and affordability. In Senior Design 2, we optimized this concept. We added IP65 enclosures for durability, extended battery life to over 6 months, and refined our LoRaWAN communication. We also developed a live web dashboard and added an AI assistant to help users make decisions from real-time data. With these enhancements, our concept evolved from theory to a field-ready solution, proving its potential to transform agricultural monitoring.
Let's walk you through a block diagram for our smart agricultural monitoring system that uses LoRaWAN for wireless data transmission. Breaking down the architecture and components, we see that the system starts with environmental inputs using sensors placed in the field to gather data. These sensors are part of the end nodes, which transmit the data to a gateway. From there, the data is forwarded to a server, where it is stored and then analyzed. This process turns raw environmental signals into actionable agricultural data. Now, let's take a look at the gateway. It includes 3 key parts: Raspberry Pi Zero with the head, or my controller, the WM1302 LoRaWAN gateway module. This handles the LoRa communication. And also we have the Raspberry Pi head with the WM1302, which connects the module to the Pi. This setup is powered via AC and acts as a bridge to the sensor nodes and the data server. Now, onto the end nodes. These include the Arduino B4 microcontroller connected to a growth-based chip. For the sensors, we have a soil moisture, temperature, and humidity and a light sensor. On the other hand, we have the FIU E5 LoRa module with an antenna for transmitting the data. For the power system, we have a lithium battery powered by a 6-volt solar panel with a charger controller and a DC to DC step-up converter for a stable power. Together, this system creates a low-power, wireless solution that collects and sends field data in real time, helping farmers to make informed decisions.
Here's our fully assembled smart agricultural sensor node. It's actively reading real-time data from multiple sensors: soil moisture, temperature, humidity, and light. The data is wirelessly transmitted using LoRaWAN, with all components powered by a solar charged battery system. Our cloud-based database sends the sensor readings to Supabase. As you can see, the data is instantly populated in real time, timestamped and organized for analysis or historical tracking. This live data is also displayed on our custom-built web app. The dashboard shows the latest sensor values, giving users an intuitive and accessible way to monitor the crop conditions remotely. To take it a step further, our built-in AI assistant provides actionable insights. Just ask a question like, how can I improve soil moisture levels? And it responds with recommendations based on the current readings and ideal crop conditions. This is smart agriculture in action: real-time sensing, cloud storage, live dashboards, and AI-driven advice, all working together to support better farming decisions.
Oh, hi. I was working on our project. Do you want to know what it's about? Oh, okay. Imagine you have an electric vehicle and you park it and it instantly starts charging without having any cords or cables. That's what we're designing here, a completely wireless charging system.
This is the charger enclosure, built using custom fiberglass molding we commissioned through CMDT Manufacturing in Texas. It's rugged, weather-resistant, and designed to house the entire wireless charging system. From a messy image to this efficient, organized design, we mounted inductive coil in the heart of our system, where the power happens. It creates magnetic field that transfers energy wirelessly to a receiver mounted under the car.
What's our goal? Making EV charging feel like magic. No effort, just park and power up.
It is the same principle as your phone's wireless charging system, except just scaled up a little, that handles thousands of watts safely and efficiently. I'm Artis Sangun from Team 13, and this is our wireless EV charging system design. Thank you for watching.
Oh, hi. I was working on our project. Do you want to know what it's about? Oh, okay. Imagine you have an electric vehicle and you park it and it instantly starts charging without having any cords or cables. That's what we're designing here, a completely wireless charging system.
This is the charger enclosure, built using custom fiberglass molding we commissioned through CMDT Manufacturing in Texas. It's rugged, weather-resistant, and designed to house the entire wireless charging system. From a messy image to this efficient, organized design, we mounted inductive coil in the heart of our system, where the power happens. It creates a magnetic field that transfers energy wirelessly to a receiver mounted under the car.
What's our goal? Making EV charging feel like magic. No effort, just park and power up.
It is the same principle as your phone's wireless charging system, except just scaled up a little, that handles thousands of watts safely and efficiently. I'm Artis Sangun from Team 13, and this is our wireless EV charging system design. Thank you for watching.
What if you could see exactly how much energy your home is using in real time?
This is the Power Pulse. It doesn't just monitor your energy consumption, but it also changes the way that you use power.
Unlike conventional monitors that give you data after the fact, PowerPulse delivers instant readings to this display and transmits everything securely to the cloud.
Now watch what happens when I simulate turning on a high energy appliance.
The average household wastes up to 30% of their energy without knowing it. With PowerPulse, users typically save 20% on their monthly bills while reducing their carbon footprint.
It's like having an energy expert in your home 24/7.
PowerPulse. Smart power for smarter planet.
Installation takes minutes, not hours. No complicated wiring, no headaches.
PowerPulse. Take control of your energy.
Because when you see it, you can save it.
PowerPulse is a revolutionary home energy monitoring system that displays consumption in real time. Our system helps homeowners save money while reducing environmental impact. Features include on-device display and secure cloud data transmission. The mobile app gives user detailed insights and control from anywhere. Our goal: make energy management simple, effective, and accessible to everyone.
We evaluated 3 potential concepts using weighted scoring criteria. Key factors included accuracy, installation simplicity, data accessibility, and cost. Our hybrid solution scored highest in user experience and data granularity. Original concept enhancements in Senior Design 2 are the added cloud connectivity for better data access, implemented robust security protocols, and developed cross-platform mobile application.
Our main monitoring unit can be installed on any device. Displays real-time power consumption for the entire home. Works with high energy appliances.
So our inputs are going to be the plugs that we measure. So they are going to measure our current and power levels by picking up an electromagnetic signal around the wires. Our processing is going to be the Arduino-based microcontroller ESP32 running the C++ code in the IDE called Platform.io, as some call it. Our outputs are going to be an LED display and a cloud-based data analysis that eventually displays to our app. So we have a data architecture and we have encrypted data while it is being transmitted to AWS and Azure using MQTT protocol. And our DynamoDB is where we're storing the database in, and we're using S3 buckets and blob storage in Azure. So AWS uses Lambda functions to handle processing in our data, so it takes load off of our microcontroller. And secondary monitoring devices in Azure, they help the blob storage. With our dual cloud approach, it provides redundancy and specialized processing. Now for our mobile application. It's built with React Native because it is cross-platform. It is a framework built by Meta, and it works on iOS and Android. Its features include real-time monitoring, historical data analysis, and security. And we use insights based off usage patterns.
So our mobile app shows averages of power metrics. Our dashboard shows current and historical usage patterns, Our device recognition IDs isolate specific appliances, and then we have wireless updates using air transmissions and Wi-Fi.
Some of the key advantages over conventional monitoring systems would be real-time feedback, as well as monthly summaries, appliance-level insights through pattern recognition, cloud architecture, which allows continuous improvements in testing that shows 15 to 20% typical energy savings, and installation takes minutes rather than the hours installation of our conventional energy monitoring systems. Not to mention, there is future prospects of being able to integrate with smart platforms like Google Home, and Alexa.
A quick intro into our project, the Inline Network tab. The main focus of the Inline Network tab is to sit in between two devices to collect networking data. With this networking data, we'll be using AI to interpret all the packets being captured by our Inline Network tab.
This is our environmental setup. We have our monitoring PC on the top left that is connected to our FPGA on the bottom left. The FPGA board is then collecting data from the victim PC on the bottom right.
On the left-hand side of the screen, you'll see a packet capture that was done with the board. The board listens to the information that's being passed around the network and then sends that information over to my local machine. On this machine, I can then pass that information to the Anthropic API, and the AI will then give us an interpretation of the network information. So it looks at things like the traffic patterns, what protocols are being used, the time that they were used at, and gives us security implications. Finally, it gives us next steps to investigate the security implications of the data.
Hello, we're the members of Group 15 and this is our senior project, an inline network tab. In simple terms, it's like a security camera for your internet traffic. It silently monitors what's happening on a network without disrupting anything. Cybersecurity engineers use this to detect threats, troubleshoot issues, and keep data safe without anyone knowing it's there. It's reliable, easy to implement, and completely invisible to the network. A small device making a big impact.
Our original concept selection allowed us to choose the Spartan SP701. The board had two RJ45 ports, was able to operate at 1 gigabit per second, and allowed us to use both wireless and serial for monitoring. Here's our original concept. We were using both RJ45 ports to sit in between two devices and intercept communication. We were also using a serial port to send the data to the monitoring computer. In the end, we decided to go with a single RJ45 port set to promiscuous mode to pick up traffic all across the network, and rather than serial, we also used wireless transmission of data over SSH. Here are the two concepts side by side for comparison. Let's look at the data flow for our program. First, the network traffic is captured by the PC Ethernet port. The raw bits are transferred to our tap sniffing program written in C. That C program generates a PCAP file, which is transferred to our monitoring PC via SSH. That PCAP file is then summarized into a clean JSON format. That JSON data is then sent to the Anthropic API, which then provides us with an analysis result. Let's take a closer look at the tap sniffing program written in C that runs on the FPGA board. The packet capturing program starts by initializing an interface and then opening a live capture. The PCAP headers are added to each packet that's captured across the network. The entire time the program is waiting for a signal interrupt so it can finalize the PCAP file and exit. Now over to the JSON summarization portion of our data. Python script starts by allowing the user to choose either a JSON or text output, which is human readable. Then we read the PCAP using the pyshark.file capture, which is a module that uses the Wireshark command line interface in Python. Then we loop through each packet, extracting the relevant information fields. We then have a data structure that aggregates all of the IP information, such as bytes, destination, and protocols. Finally, we take that information and form it into percentages so that they're easier understood by the LLM. Finally, we output that to JSON. Here we can see the device booting in its initial state. On the right-hand side, you'll see the FPGA board. This is a serial connection, so we're able to see the kernel boot from nothing. As the kernel boots, you'll see the different RAM devices being initialized and the Ethernet. Finally, you'll see the Dropbear SSH server generating an RSA key, which allows for SSH connections. Here's the output of the uname command showing that we are booting on the Microblaze architecture of our FPGA board.
Now let's watch an actual capture in progress. We issue the capture command over SSH to the board, and we authenticate to the board. This allows us to pass the capture files back and forth to our monitoring computer and the board. Then, in the bottom right, we generate a fake attack. What this does is generates malicious traffic patterns using a Python script. Now we run the AI packet analysis. We send the PCAP file over to our AI script, which then analyzes the traffic. So here you can see that the AI has produced traffic pattern analysis, protocol, destination, and security implications. Finally, it also gives us some recommendations for future remediation.
My name is Mike McChesney. This is the Lander Challenge main avionics PCB. The purpose of this PCB is to lower the barrier of entry to self-landing rockets by reducing both the cost and complexity. This avionics board features fully integrated IMUs and magnetometers for measuring the acceleration as well as the rotation of the rocket or lander during flight to understand where it's flying to and how to land it, as well as critical health metrics such as tank pressure, engine temperature, thrust during flight, as well as a transceiver to send and receive data with the ground station so it can be monitored during flight. Thank you. This project ended up being extremely ambitious for our experience level. Designing a full PCB from scratch was a lot, and while the board does include everything that we originally said it would, including the IMUs, magnetometers, the ADCs, all for the data collection, as well as the transceiver and antenna for sending it back and forth. And we've been able to connect to it and upload programs and show that with blinking LEDs. We haven't been able to get information back from the board currently because of the Ethernet. There's a picture below that'll show the waveform that we're getting, which is 50 megahertz, but is not a clean square wave. And because of that, the Ethernet isn't able to send and receive at the moment. So we're working with Dr. Zakios on this problem for showcase, but unfortunately for this video, we haven't been able to get a demonstration.
Hello, my name is Gabriel Allen, and I'm a member of the Lander Challenge main avionics PCB team. Our project focuses on designing and assembling an avionics board to control a lander engine being constructed by a mechanical team. Alright, so we see a picture here of our avionics board as well as the power management board and the rocket engine itself. So we'll get right into, let's throw back to what we did initially in Senior Design 1. Why did we choose to go with an STM32? We have to look back at our original criteria. We placed a premium on real-time performance, followed by speed and heat resistance, reliability, and coming in last was cost. The three options we considered were the Teensy 4.1, the ESP32, a custom-designed board around that controller, and a custom-designed board around the STM32 microcontroller. In our research, we had found that the STM32 microcontroller offered the best performance in terms of real-time performance, speed, and reliability and heat resistance. Although it was the most expensive option, cost was our last consideration, and so it didn't play a huge role in this. Here we see the original block diagram as drawn out in our Senior Design 1 course. The power management board is virtually unchanged and is basically a finished product. Our servo valves, sensors, and solenoids remain unchanged as well. And on the right we have the avionics board. Now we did make a change to that avionics board. In addition to the 900 megahertz transceiver, we added an Ethernet controller and an RJ45 socket so that we may transmit and receive data over a wired connection. Finally, here is the block diagram for our STM32 microcontroller, the avionics board itself. It pulls in data from the two analog to digital converters, taking in the sensor data. It takes in orientation data from the inertial motion unit and the magnetometer. It can transmit commands to the fuel tanks, pressurizer tanks, and oxidizer tanks, as well as the ignition system. And finally, commands can be received and data transmitted through either the wireless transceiver or the Ethernet controller. At the center of it all is a custom STM32 microcontroller board that it has custom firmware to handle all this processing. So that's our system so far.
This project ended up being extremely ambitious for our experience level. Designing a full PCB from scratch was a lot, and while the board does include everything that we originally said it would, including the IMUs, magnetometers, the ADCs, all for the data collection, as well as the transceiver and antenna for sending it back and forth. And we've been able to connect to it and upload programs and show that with blinking LEDs. We haven't been able to get information back from the board currently because of the Ethernet. There's a picture below that'll show the waveform that we're getting, which is 50 megahertz, but is not a clean square wave. And because of that, the Ethernet isn't able to send and receive at the moment. So we're working with Dr. Zakios on this problem for showcase, but unfortunately for this video, we haven't been able to get it done.